technology journey, many of you, and that's a journey to destination zero. So our planet faces a tremendous challenge as we face the realities of climate change. And Cummins is focused on doing our part to address air emissions and climate change in line with science, and specifically that our customer success is powered by carbon neutral technologies that address air quality. And this is the focus of Destination Zero. So before we get into the topic, let me give you just a little bit of an overview on Cummins. So we are a global power leader that designs, manufactures, distributes and services diesel and alternative fueled engines and powertrain related components and products. And that includes transmissions, electric power generation systems, batteries, electrolyzers, hydrogen fuel cells, hydrogen storage tanks, and electrified power systems. And Cummins is over 100 years old, and technology innovation has been at the core of our products since the start. We are investing in a number of different powertrain technologies, advanced diesel, natural gas, hydrogen internal combustion engines, or ICE, and you'll hear us use that phrase and you'll see it throughout the package, just a shorthand because internal combustion engines, that's kind of a mouthful. We're also investing in low NOx gasoline engines, propane engines, battery electric, and hydrogen fuel cells. So it's important that we recognize the diversity of investments that we're making because you are all going through very similar things yourself. There isn't a single solution that will be the power provider of the future. It's really hard to replace diesel. It's quite versatile. And so it's going to take an array of solutions as well as low carbon fuels to achieve the climate change goals that we're all trying to achieve. As we get into the topic of hydrogen engines, I think it's important to talk about hydrogen engines and also hydrogen fuel cells because they are two complementary technologies that each have different values, and they both have a role in the market. So I thought I'd walk through that first, even though we're going to focus on the technology on the left. Want to at least baseline the group on hydrogen fuel cells. So these are both technologies that use 100% hydrogen fuel. And let's start on the right with the fuel cell. So it is a 100% fuel powertrain. It has a fuel cell stack that is installed typically under the hood, but it's in this example, it just happens to be a Class 8 kind of North American truck, and there's a large open space when you don't have an engine. And that fuel cell takes hydrogen and converts it into electricity. That electricity is used to run electric traction motors, and also it's stored in batteries to help buffer the power and supply on-demand power and torque when needed through electric traction motors. The fuel is stored in hydrogen storage tanks, similar to natural gas vehicles today, and we'll talk quite a bit about that technology and that system because it's common with the hydrogen engine on the left. Hydrogen fuel cells have 100% tailpipe reduction of CO2. It also has 100% reduction of NOx emissions. It is also more efficient in the 10 to 15% kind of from a fuel bill perspective. And so it is a great technology. There's a lot of value in hydrogen fuel cells, and it's one of the many that Cummins is investing in. On the left is a hydrogen engine powered vehicle. It's a very traditional type of installation. The engines that you'll learn more about today are installed where an engine is installed today. It mates with current transmissions and uses current cooling packs and accessories. So that's pretty common with today. The main difference is the fuel storage. That hydrogen fuel storage, like I said, is very similar or is similar to the fuel cell vehicle. It has a 99% plus tailpipe CO2 reduction. And so you might say, why is it not 100? There is a little bit of oil carryover that from the carbon can make its way through to the tailpipe, but at a system level, still the tailpipe reduction is over 99%. So it's a fantastic CO2 reduction technology given the simplicity of the system. There's a 75% tailpipe NOx reduction from today's diesel vehicles. And I should point out that diesel has already reduced NOx emissions by 90% over the last decade or so. So that's quite a bit of NOx reduction. These are extremely low NOx levels. It also is the lowest initial cost vehicle from the zero carbon fueled technology. So those three in my mind are hydrogen internal combustion engine powered vehicles, hydrogen fuel cell vehicles, and battery electric. So a lowest initial price. It has a very high technology readiness. We can be in scale production of these vehicles in 2026, 2027, somewhere in the world, in which we'll talk more about today. And also it's a relatively low complexity chassis integration. because it's a pretty conventional vehicle and a conventional powertrain. The Cummins new fuel agnostic engine platforms that we'll talk a bit about also help pave the way by reducing the complexities on the chassis integration from switching to one fuel type to another. Not to say this engine runs on multiple fuels. This is a dedicated hydrogen engine, but it shares a lot of components with other fuel types. So while I mentioned there's a efficiency difference between the two technologies, there is a significant lower cost, like I mentioned, for the hydrogen engine powered vehicle. And so if we look at kind of a TCO analysis of a model year 27 type of vehicle, we would see TCO parity between the two products in the 5 to 12 years of operation, depending on the miles driven and then also the fuel cost. So that range includes fuels for hydrogen, green hydrogen, in the range of $4.75 to $7.50 US dollars per kilogram. And I just think that's important to note that there is it's a much lower initial price. Fuel cells are more efficient. And so if you really drive the miles, in the 80 to 120,000 miles a year, then you can break even after about 5 to 12 years, depending on the fuel price. The final comment I'll make here is that you'll see a number of images of North American Class 8 trucks in the package. And that's just because that was a graphic that was available, but it's also an area of the market that's developing quite quickly. But that doesn't mean to imply that the technology is not applicable really quite broadly wherever diesel engines are used. And we'll be talking about that as well today. So Cummins has announced that we're working on 2 hydrogen fueled internal combustion engines, a 6.7 liter and a 15 liter for global on-highway and off-highway markets. And as we look at this technology, and you ask why, why are we doing this? Essentially, Cummins and the industry, we're all working towards a common goal, and that's decarbonization. However, significant uncertainty exists. Uncertainty on which technology is the right technology, when will different technologies achieve maturity, when will fuel prices come in the range of viability, fueling infrastructure. So there's just a lot of unknowns. And Cummins is actively exploring the hydrogen engine and building market interest because we see it as a very practical zero carbon fuel technology. It takes a lot of what we know and then it adds a new element, hydrogen. That's the new key here. The rest of the system has significant industry knowledge around it. And so we also feel that investing in multiple zero carbon technologies is critical to ensure customers have options and competition exists. And finally, we're receiving a lot of interest, and that's because of the low initial cost and commonality with current powertrains. So as we look at the overall kind of operating space for products, this cartoon I've seen kind of reproduced in many areas. You'll see many companies have different versions of this. There's a significant place in the industry for battery electric vehicles and battery electric equipment. And there's usually, and those are in applications and duty cycles, et cetera, that are typically low on the asset utilization, so either low mileage or low hours per day. And then there's other, that are less obvious attributes around the operating environment and infrastructure. But there's also a place where depending on how the asset's used, a battery electric solution isn't practical. It could be a range, weight, it could be a duty cycle, or access to infrastructure, a lot of different reasons. And we need other technologies to pick up. And we see those technologies as zero carbon technologies as hydrogen fuel cells, hydrogen engines, renewable natural gas, renewable propane, renewable diesel. There will be quite a lot of diversity, but like I said earlier, we need that because of how we have to replace, fossil fuel-based diesel, which is just ubiquitous. It's low cost, it's reliable, it's very versatile, and so it takes a lot of options to overcome and fill the full space for our applications. So we're aggressively pursuing 2 engines in that space, one at the low end of that chart on the left, one at the high end of the chart on the right, so a 6.7 liter and a 15 liter engine. We're looking at it globally. A number of markets are under review. This changes quite often, as we work with customers, OEMs and users on the technology, and different markets are starting to bubble up as they could be quite compelling. There seems to be some interest. in different global on-highway markets as well as off-highway. And again, this changes weekly. If you don't see your application on here, that doesn't mean it's not prioritized or anything. It's just we're just trying to reflect the different interest that is starting to show and where customers are leaning with these two engines. As the market grows, I think there's also an opportunity for an engine in the middle between these two. Cummins has them in our portfolio, and that could also be something that follows these two, but these are really kind of in the lead, I would say. So a little more detail on the two engines. You'll notice power and torque are quite similar to the equivalent diesels today. And then I've got some weight and dimensions. We're also focused on leading emission levels globally. The power and torque numbers, like I said, are quite similar to their equivalent diesels today, and that's really for two reasons. One, these are based on Cummins' new global platforms that have kind of entitlement, efficiencies, entitlement weights, and really low friction. So these are new, very, very modern engine platforms that have been designed for the future, and they've been designed in a fuel agnostic way, which we'll talk about on the next slide. So one key is these are new platforms with a lot of capability, and then the second is the architecture that Cummins is using. So our hydrogen engines will have a pent roof cylinder head with tumble combustion. These are spark ignited engines with direct inject. They're lean burn, and that means they will have more of a diesel-like aftertreatment with SCR. But this direct inject architecture, coupled with these platforms, gives us very high efficiency as well as really capable power and torque. The competing technology is a port fuel injected version, and you'll see things in the press from others. They are investigating port fuel type of architecture, but that won't deliver the power and torque, we don't believe. And so we're really excited about having this competitive architecture out of the box. Like I said, these are based on Cummins' new fuel agnostic platforms. And what this allows us to do is have very common engines from the cylinder head down. And so we can drive a lot of global scale, reliability, durability on these common components that are common between diesel, natural gas, hydrogen, as well as gasoline, propane, any fuel that we want to use. The base engine, that platform is common, and then we have a different cylinder head and associated components to handle the difference in fuel. That's a great story for, again, that just global reliability, durability, as well as installation commonality, because once it's installed in a chassis, then the switch between fuels is a lower integration. It's more of a fuel system and getting fuel and onboard storage of fuels, et cetera, to the engine. But there's a lot of commonality in the platform. In the case of hydrogen, we will typically see things start their life as a diesel. Maybe that progresses to spark ignited through natural gas and then ends in hydrogen, but each platform will take somewhat of its own journey, but the concept holds around commonality from the cylinder head, below the cylinder head. So as we start to explore the why hydrogen ICE a little bit further, and so we do feel that fuel cells could be a long-term solution for decarbonization in many applications. It's just that a hydrogen ICE provides a really complementary short and medium-term solution. First, it starts with the fuel. It's a zero carbon fuel technology. Also, we can go fast. We can be in scale production mid-decade, and that's just because of the maturity of the technology. We're working in an industry that has an entire supply base that's ready to go for an engine. We can produce at scale levels, as well as the vehicle integration points and the vehicle accessories. The industry is set up for this. We can go fast with it. It can be in production in a very reliable, controlled way. There's a lot of benefits for the end user as well. Like I mentioned, the initial low cost compared to all of the zero carbon fuel technologies. It's also a drop-in replacement with respect to their operation. It's very familiar powertrain technology, vehicle technology, maintenance practices. It still requires oil changes, things like that an engine would require. So very common to current practices. We also hear from customers about a single fuel supply switch. So as an end user, they're trying to figure out what's my next thing? And they want to pick, if they move to something, they don't want to have an intermediate solution and then have to change again. That's just a lot of work. And so they'd rather what's my final supply? What's my final fuel? And the engine gives them a path to have hydrogen as a final fuel. They can use it now with an engine, and they can migrate as fuel cells come reach their maturity as well. And that becomes an option. They'll have two options for hydrogen fuel. And there does appear to be a lot of consensus around hydrogen fuel as a final commercial fuel for both commercial vehicles and equipment. Also, the technology is quite complementary to fuel cells. The fuel tanks that we'll talk about in a minute are common. It's the same fuel tank for a fuel cell or an engine, and the consumption technology on the vehicle don't care. They just need hydrogen, at the fuel cell or engine, and that storage system is the same. So going early with engines can help drive scale and cost out of those systems, further driving adoption. It also drives fueling infrastructure, and we can have consumption technology to match with the hydrogen generation technology at a fast rate, so we can go fast and help justify that infrastructure investment. And finally, it helps with the service infrastructure. So we always have to keep in mind the service and support aspects of this equipment, and any kind of upgrades you do to facilities to handle hydrogen as a fuel. It's the same infrastructure with hydrogen sensors in the service bay or whatever. It's the same because you're working with a new fuel called hydrogen. So the facility upgrades are common. So we can go early, drive that investment, but you can diversify with multiple powertrains using this investment. So we have a lot of data on various elements that we'll start to walk through at a high level, but I'm going to happen to use the 15-liter example, I think, in most of these, and it'll happen to be mostly an on-highway example as well. So 15-liter engine, the specs are common to the Cummins 15-liter efficiency series, 400, 500 horsepower, torque in the 450 to 1850. Fuel economy is route dependent, but we think it'll be about 6.25 miles per kilogram of hydrogen. Because we'll have a diesel-like aftertreatment system, there'll be a SCR. The DEF consumption rates will be very similar to diesel. The weight you can see of the engine of a dry weight is here. This is the new 15-liter platform from Cummins, so it actually has quite a bit of a weight reduction from the current X15 efficiency series that you know and love today. I already quoted the CO2 and NOx reductions, and there's a little box in the right. If I use the EPA's greenhouse gas emissions model and estimate the savings, CO2 savings per year from a hydrogen internal combustion engine in a typical Class 8 truck, that's a lot, right? There's 1,437 fewer metric tons of CO2 over the lifetime, and 144 fewer per year. So significant savings that can result. I mean, this is the same number you would get from a battery electric or a fuel cell. So dramatic savings, and that for OEMs, for the truck makers that actually have to do greenhouse gas modeling and hit certain criteria and levels in that model, this provides them a fantastic lever to help with their CO2 reduction targets. In an on-highway spec, this is a typical large fleet spec with a sleeper cab. Happen to pick a typical rating, 450 horsepower. This would come with the Eaton HD and XD AMT transmissions. We'd be speccing it for a 500-mile range. You can get larger ranges. It's just more tanks, and that adds costs, and we'll talk through that in a little bit. Base engine warranty would be no different than a diesel. And also the durability is the same. That question comes up a lot. The engine goes through the same validation, the same what we call standard work at Cummins to validate any engine. And so there's no difference because of the fuel type, and it's based on a lot of the diesel components anyway. The vehicle weight, this vehicle would be about 2,500 pounds more than a diesel. And today there's already an allowance for natural gas vehicles, a 2,000-pound allowance from the Department of Transportation, and so that you're not penalized from a cargo perspective because of the increased powertrain. So an 80,000-pound vehicle can actually haul 82,000 pounds if it's a natural gas. We expect the same allowance, and we're working on that actively to get that allowance for hydrogen so that you're not penalized for the additional weight. And why, you might say, well, why is this weigh more than a natural gas vehicle? It's really the tanks. that we'll talk about in a minute. The tanks are higher pressure. They have capacity to store fuel at a higher pressure. Therefore, there's more carbon fiber windings on the tanks, and then they weigh more. From a price, you've heard me mention a couple times that the initial price of this vehicle will be lower. And so here's a graph that shows that diesel is always going to be the lowest cost. So as we forecast 2027 costs for different technologies, diesel is always going to be the lowest. Renewable natural gas would be next, and there's a lot of cost in the fuel storage system that drives, vehicle level cost increases. Hydrogen will be more than that. These are more expensive tanks. They'll be low volume for a while. And so there will be more costs in the system. But if you look at the 3 zero carbon fuel, you'll see hydrogen fuel cells is next, and that's the gray is the 27 forecast, and then you can also see battery electric. And you can see those are higher, and it's a newer technology. They're working on their maturity curves. There's a lot of cost they need to come down in the fuel cell itself, batteries, etc. And they will over time, and they have a larger chance of reduction over the years because of as they reach maturity, their cost should come down. Whereas a hydrogen engine will be relatively stable because it's based more on mature technology, just like the natural gas and diesel. I did include a battery electric here. I just wanted to have apples for apples. So this battery electric, at least in the bar chart, is spec'd at this, a 27 spec with a, that would drive a sleeper cab, 500-mile range. While that's probably not the most practical vehicle layout you would have because of the charge time of that battery pack, which would be quite significant, and the weight of the battery pack, it really may not be a practical solution. I did want to include it just for completeness in that study. I've got a slide here on maintenance intervals as well. Maintenance intervals, it's going to be very similar to a diesel engine, except there's a spark plug. So that's more common with natural gas. And the DPF clean is something we're still working on. We believe there will be a DPF. There's very, very low soot generation, but we're working through the studies now to understand what the filtration requirements would be, and then what would the regen frequency be, if any, or not the regen, the cleaning frequency, if any. But there's a DPF maintenance lamp today with our products, and it would be there tomorrow likely. But we just don't have a kind of a range yet that we could forecast. But otherwise, very common with internal combustion engines, diesel or natural gas. And then the fuel delivery system. So like I've said a couple times, the fuel delivery system, the storage tanks, the high pressure lines, the valves to reduce it down to pressures that the engine would need are compatible with both hydrogen engines and fuel cells. And so I think that's a great point for a vehicle integrator. As you integrate hydrogen, you're integrating it once, and it can be leveraged for both an engine or a fuel cell. So the re-engineering doesn't have to occur 2 times. If you kind of commit to a hydrogen, vehicle, you've got then options if you could do engines or fuel cells. These are type 4 carbon fiber fuel tanks. Storage pressure, typical, I'm seeing 2 nodes develop at 350 bar and 700 bar. We're seeing fueling stations kind of support those 2 different pressures. And it's on vehicle, to me, it's just cost and range. The 700 bar will cost more, but you get more range. And I think it's more application dependent on what you would want to do. But those are 2, at least, I hesitate to say standards because I don't know that that's really true, but just there seems to be alignment, and people talk about those 2 pressure nodes. Those are much higher pressure than natural gas is today. Natural gas, I believe, is more like 150 to 250 bar. That's just based on memory. And then configurations, this, you can see the back of cab structure here. There's also options for saddlebag where the diesel fuel tanks may have been, at least in this image. And then I think there'll be a lot of custom things depending on application. But we'd like to standardize on at least some tank dimensions, because each tank dimension, if you can commonize on part numbers, then you can continue to maintain lower costs. But the more, you don't want to proliferate the tanks themselves into too many configurations. That just adds a lot of cost. There are some safety standards out there, and this is not intended to be a complete list of standards. I just wanted to reference at least a couple that are out there with respect to, in general, pressure vessels and high pressure systems on vehicles. as a reference to just acknowledge they are out there. The industry has been dealing with natural gas high pressure systems for some time. We've had natural gas engines in production for 20 years. So there is a lot of experience that already exists with onboard gaseous fuel type of storage and systems. And so we've talked a lot about engines, but I did want to raise awareness that Cummins also participates really in the entire hydrogen value chain. We have hydrogen production technology with electrolyzers. We do have hydrogen storage at very high pressures, 1,000 bar for stationary storage, as well as mobile 700 bar. We have experience with dispensing. We also have both consumption technologies in our portfolio, be it fuel cells or hydrogen engines. And then from a product introduction timeline, the timing is a question that we get often. So to help facilitate that, I've added a directional thought that we have, at least for the North American market, for US, Canada, is that we are in the middle of our R&D work now, and we're looking to kick off our product development cycle early next year. For both engines, for our 15-liter and the 6.7. We expect to have pilot level and demo level vehicles and equipment running in 2025. But this is in the 1 to 10 just globally. And then we would move into our typical field trials in the 25 to 20 and 26 timeframes as we're leading into full scale production in 27. So, this is a rapidly evolving, I'd say, scenario. There's a lot of uncertainties that still exist. We don't have final emission regulations yet for 27 in North America from the EPA. And so, there's a lot that's in flux, but this is directionally where we're headed. I just want to make sure that you understand it could change as we learn more. And also it depends on customer interest, OEM interest, and also end user interest for this technology. But this is something that we are considering a launch around the 27 timeframe, full scale at capacity. This isn't, when I say scale production here, I'm not talking hundreds of units. This is capacity of 10 to 20,000, just depending on what the market needs. First fit, you could order it from an OEM. These aren't aftermarket upfits or anything like that. All right, with that, I'm going to hand it over to Hui.
All right. So thank you, Jim. Can you hear me okay?
I can, yes.
All right, thank you. Yeah, if you can go to the next slides, please. So some of them Jim already covered, but realize we never defined what's a hydrogen engine, right? I think for this audience, probably we don't need a definition. The hydrogen engine essentially is the engine burning hydrogen as a fuel, essentially, right? So for the technology we are developing here on the hydrogen engine, we think is a spark-ignited engine variant. For that matter, it would be similar to natural gas and gasoline. And in terms of the combustion process is more different from diesel, right? So but with that, it can utilize the existing installation capability in the engine and component manufacturing. We think this is going to extend the internal combustion technology to beyond 2040. I have two tables here, and Jim already touched many of the aspects of things. I wouldn't repeat everything he has already said. But on the high level, you look at it between diesel, hydrogen, and other spark-ignited engines, you would share the same block and installation parts, right? So the vehicle integration aspect, the durability from the base engine, you're going to enjoy that for the diesel engine's durability. However, the hydrogen engine, our technology development was based on the existing spark-ignited engine like natural gas and gasoline, right? So we will use the cylinder head from those existing technologies and tailor for hydrogen. That means you would enjoy this dual overhead cam and the variable valve train actuation, all those kind of things. Ignition systems would be largely the same between the spark-ignited engines. The engine ECM and software would benefit from the existing models that we have on the spark-ignited engine. What is unique is going to be the fuel system and air handling system, and I have more details coming. We are assuming the lean burn would be the path for its superb power density and efficiency that it would offer. As Jim mentioning, if that's the case, we would assume the diesel-like after treatment would be used for us to ensure the emissions compliance. And fuel cell and fuel hydrogen engine, they would share a lot of commonality, but there's one distinct difference between the two is the energy conversion mechanism, right? So the hydrogen fuel cell uses the electrochemical process. It is more efficient compared to the hydrogen engine combustion process, but it's a slower process compared to combustion. So if you look at the fuel cell, most of them you see those are electrified powertrain. Hydrogen engine can enjoy the benefits from electric powertrain. For example, you can harvest the waste energy, but for the technology, hydrogen engine technology we are developing, we are targeting for an engine standalone solution. But it doesn't mean in the future we couldn't electrify the hydrogen engine and give you even more benefit, right? So in terms of power density, efficiency, transit response, all those kind of good things, electrified powertrain would offer. And because the fundamental conversion is different, hydrogen fuel cell doesn't generate criteria emissions, specifically NOx, NOx. Hydrogen engine has combustion process in there. It generates much lower NOx than other engines you would know of, but it still probably require some after treatment so that we can meet the global emissions compliance requirements. So this slide, I'm showing a lot of technical data. I do not plan to go through each one of them, other than I will highlight some unique property on the hydrogen, and those properties are relevant for the coming hydrogen engine architecture discussion. So let's go through that really quick. So I divided those properties into two sessions, right? One is a thermophysical property. So for example, there's no carbon in the fuel. For that reason, it's considered tank to wheel greenhouse gas technology in there. It has really high mass-based lower heating value. It's higher than, almost 3 times higher than other conventional fuel you would use today on the market. So if you have access to liquid hydrogen, if it's going to give you really good mileage range, right? We don't see that going to be mainstream anytime soon. But because of the high mass-based lower heating value, that's one of the reasons, even NASA using liquid hydrogen as their rocket fuel, right? So that's one very unique property of hydrogen. For the ground transportation, we think that the gaseous or compressed hydrogen most likely would be used in there. As a gas, though, hydrogen has a very low volumetric based on lower heating value. That's our major consideration when we design the hydrogen engine fuel system. Another one, the thermophysical, is the air-fuel ratio is high, meaning for the same mass of fuel, you need more air, right? So that's a direct impact on our air handling design. So again, there are more details coming. On the combustion side, not everything is independent. There's a lot of interdependent considerations. So let me just briefly touch several of them. Hydrogen actually is very difficult to autoignite. So if you look at the autoignition temperature number on the right table, you would see the autoignition temperature at the same pressure, hydrogen is higher, meaning it's actually pretty difficult for us to be compressed ignited like a diesel engine. However, it has pretty low ignition energy, so that's a great for a spark ignited approach in there. It has a pretty high flame speed and very wide flammability limit, meaning you could run very lean and a very wide range of lambda, or use EGR, or in combination of them, right? So you could do a lot of things because of the easy to ignite, and they can burn really fast, and you can ignite that charge and have a reliable combustion on a pretty wide range of lambda or EGR in there. And also, it doesn't all want to auto-ignite. So you actually have pretty good auto-ignition or knock margin for this engine. For that matter, hydrogen is really very suitable for spark-ignited engine application, right? However, there is an ignition aspect of things. Many researchers would run into the pre-ignition issues because of the low ignition energy. And we have been doing a lot of work in that space, and we will explain a little bit how we do that. The last two points on this list is the hydrogen has a pretty small quenching distance, hydrogen flame. So for that, for safety considerations, we will try to not to have any hydrogen air mixing upstream of intake valve. And hydrogen has high flame temperature only at a stoic, right? If you could run hydrogen lean, then your temperature is way much lower than other fuels you would experience, and the benefit there is obvious, right? So you wouldn't generate as much of NOx, and you wouldn't also have a lot of heat rejection. So those are on a high level, hydrogen's unique properties. So Jamie, if you don't mind, go to the next slide, please. So here's the hydrogen engine architecture considerations here. What I'm showing here is the red boxes I'm showing, those are the challenges. The challenges related to the hydrogen unique properties. And the green box I'm showing the solutions or the effort that we're working on that. So the first one, just recall the hydrogen fast flammability, small quantum distance, and also very low volumetric lower heating value, right? So we decided to choose the directly injected gaseous hydrogen as our fuel system other than other like portfolio injection or intake fumigated hydrogen from safety point of view, but also for the targeted power that we are intended to offer, and potentially can give us a great efficiency in there too. Now, the hydrogen direct injection would have a really high gas velocity. Just to put this one in perspective, the gas velocity close to the injector could reach around Mach number 3, right? So that's comparable to the world's fastest airplane, right? You can find today. So it's really fast gas injection into the cylinder, into a relatively quiescent air in the cylinder. How can you make sure they mix really well, right? That's the challenge, and we have a really good handle on that. I mentioned the pre-ignition knock propensity. We have a really dedicated ignition technology team. So we have dedicated coil design and spark plug so that we don't introduce unnecessary ignition to the charge. And we have really advanced base engine for spark ignited engines. So the cylinder cooling to reduce the hot spots, hot residual, and cool component to prevent the pre-ignition. We are sort of a stand on the shoulder giant in this case. We have a really good base engine to start with, right? So, but we are keeping improving even from there in order to prevent pre-ignition and knock. We mentioned the high air demand. I mentioned about the air fuel ratio and the stoic doubles the conventional fuel, but when you run lean, that even make it that air even more, right? So Cummins has a really great turbo technology business, and they are providing really advanced technology using the existing manufacturer capability. Basically, together with the valve train, we are able to provide the air demand for the really high power density, but also provide a very low NOx and great transient response. Now, with that kind of air handling system, we can also provide a great exhaust enthalpy to make sure our after treatment efficiency remains high, so that regardless of what is our engine NOx is already low, but we will further reduce that NOx to be able to meet the global emissions compliance, right? That's the goal, and meeting the global emissions compliance our minimum requirement. And we are also doing even more advanced study, right, in the after treatment solutions. Hydrogen, as you may know, on the periodic table is actually the strongest reductant compared to even ammonia. So we already have a hydrogen on board, right? We are also exploring to use hydrogen as a reductant to reduce the NOx. So that's a very advanced technology that we're working on. The power cylinder on the right-hand side and the bottom is basically the heart of the whole engine, I would say, right? So the piston ring design, the crankcase ventilation, lubricant selection, the goal there is basically to reduce both the blow-by, meaning the gas from the combustion cylinder into the crankcase, as well as reduce the reverse blow-by. When you have a reverse blow-by, you may have potential oil carryover that could be another source of abnormal combustion. So working in that area, trying to optimize both, so that we have a safe crankcase environment. And when we do that one, actually we significantly reduce the moisture, right? So you prolong the lubricant life, you don't have an issue in there as well. And ultimately, all this kind of things, fuel system, air handling, ignition system, after treatment, everything needs to work together and controlled by the ECU, engine control module unit. And hardware and software wise need to be both capable to make all those components work together to deliver your target power efficiency and such. So we have models from our lean burn spark ignited engine and diesel engine. So that's our software development, and the ECM will be more capable. However, in terms of the vehicle integration, the interface will largely remain the same, right? Except for the hydrogen fuel system related stuff. The last but not the least about the hydrogen damage, right? So when we see the hydrogen damage, normally we see the hydrogen embrittlement, erosion and corrosion from the hydrogen combustion in there. So there are risks that we know from the oil gas industry. They handle the hydrogen for years. So, however, there isn't a national or international standard. How do you make assessment on the hydrogen damage? So what we are doing there is we're working with the world-class research entities, trying to develop this assessment methodology to make an assessment, build the database to accommodate the field test data, so we can quantify the material, right, to mitigate the dates. Because the goal there obviously is to make a hydrogen technology to be a durable and feasible technology for our customers. So this is my last slide. What I'm showing here is our latest test result. The result is on our 6.7 liter engine. So I have the dash line, the blue and red dash line, they're showing our torque and a power target in there. And the two green lines is our recent test results showing that we can meet the target for both the torque and power. I have to point it out, we didn't really change any the power cylinder yet, right? We took the base engine, we put it in the direct fuel system, direct injection fuel system. We also installed an advanced air handling system in there, and that we can meet the power and torque target with no problem. So that's really encouraging. But we didn't stop here. What we are doing next is we're going to continue to optimize the power cylinder design so that we can achieve even better direct injection operation. And we will be balancing or optimizing the power density, the efficiency, and the emissions by improving the air handling system, right? So this is system level optimization. And we definitely is working really hard to develop the emission solutions so we can achieve the global emissions compliance. With that, thank you for your attention.
All right, and then I've ended with a slide for more information. Cummins does have a website at cummins.com/engine/hydrogen engines. And then also the contact names for myself from Hui, and then also Jeffrey, the local Cummins account leader. All right.
Great, fantastic, guys. Thank you, Jim, Hui, and Jeffrey for the presentation. That was pretty interesting. And for those of us that have been in the industry long enough, I seem to think that this smaller version of the hydrogen engine kind of fits between what we used to know as the B and the C series, right? It's sort of in the middle there. Would that be kind of an accurate?
Yeah, so I mean, so this is the 6.7 is the future of the B, and we used to have a C, yeah, and that was, I think, was it 8.9?
8.3 is
8.3, yeah, that's right, yeah. Yep, it had a C, and then it transitioned to a 9 liter today of an L. I know we only have so many letters in the alphabet, by the way. And so yeah, this B is kind of the new, the future, the 20-year version of the new B engine. And then so we've got a space right there in the middle between this B that you saw data on, and then the 15 at the top end where we could do one more, kind of round out that really the whole space, both for on highway, off highway, and marine applications.
Okay, it's interesting. I noticed that the torque curves that you showed earlier, Hui, it's a lot of power, a lot of horsepower at pretty much all RPMs. Is the torque curve similar to what we would expect from a diesel?
This is comparable, yeah, comparable with the diesel with the same displacement, yes.
Interesting, interesting.
Yeah.
One of the questions that came through from Thomas from New Flyer is about the efficiency and heat rejection compared to a conventional diesel. And I'm thinking he's thinking more along the lines of the size of the charger cooler, charger tubing, radiator size, radiator tubing size, those sorts of things. Do you have any feel for that?
Yeah, absolutely. So from the efficiency, Jim already showed some numbers. I think the efficiency would be comparable to today's diesel, right? For the next generation, I think both are going to be improving. So see who's going to win that game in there. In terms of the heat rejection, what we have seen so far, we haven't really mapped the full space yet, right? And also it depends on your other optimizations. But from the data we have seen so far, the hydrogen, especially when you are able to run lean, the combustion temperature is lower than diesel. So for that, I would expect that you most likely you wouldn't need a bigger radiator, right, in the vehicle.
Mm-hmm. I think that we're thinking more along the lines is, can we make it smaller?
Right. Yeah, I mean, there would be opportunity for doing that. And it also depends on what kind of power demand it is, right? So the more power is required, you probably reject more heat. So I think that is more like a more detailed customer engineering conversation need to happen.
Okay. Okay. Interesting.
It is a common question though. People think, oh, it must run hotter for some reason. I don't know if there's a stereotype or something, but yeah. So Hui, I think you're saying in general, it may run cooler. At a minimum, same, but if anything, it could run cooler.
Yes.
Okay, that's interesting. So here, this personal question is when Cummins has comes up with a concept like the hydrogen engine, what kind of a process do you have to go through in order to get to something that is compliant? Like obviously at the end you're doing your emissions testings and those kinds of things, but when this thing was just a seed of an idea, just give us a brief, what it takes internally at Cummins to come up with a new engine like this.
Hui, I know we started paper studies in 2019, but then you want to take it from there if you have any thoughts on how you'd answer that?
I mean, this is the hydrogen engine might be, I mean, I would say this is a research, right? Hydrogen engine has been started many times before, right? For those people around there, many times the previous peak was between 1990s and 2010, right? There's a lot of research in there. Inside of Cummins, hydrogen has been always part of our technical portfolio, right? So for example, for our off-highway market, we have a lot of interest to burn whatever fuel available to them. Many of those kind of fuels are actually hydrogen rich. So for example, some syngas for power gen, right? So we have been dealing with hydrogen all the time in there. The hydrogen engine, what we have been doing, like Jim was saying in 2019, 2020, we actually got a little bit of internal funding, could be able to allow us to run with this really optimized sparkling engine platform. The result is really encouraging, right? So we took the learning. Obviously, there are a lot of research opportunities still in there, but the performance is really encouraging. And because of that, we're getting a lot of interest. The recent, I would say, the Europe and China legislation directly resulted us, the British government that actually provided 14.6 million English pounds of funding to sponsor Cummins and partner develop the technology. And that's as a result of our current today's global hydrogen engine development program. Jim and I, we are working on that. So.
Interesting.
And the next phase of that is really the commercialization, the product introduction to the market. So we would take what we've done in our advanced engineering R&T organization, and then we move it into a stage gate process where we formalize, ramp up suppliers, and we do the final the calibration work, the emissions compliance, which takes a long time. It's a multi-year process that also involves working with the OEMs to do the chassis integration and they're going through their serialization process as well to get it to production. So it's a the step forwards are quite a bit. It's a 3 to 4 year process to get it to be orderable by a customer as a first fit solution.
Interesting. Yeah, the one thing that as you guys were going through your presentation came to mind was a lot of trucks and urban buses, for instance, they go through midlife rehabs. And the potential for switching something from diesel to hydrogen in a midlife rehab might actually be possible with a technology like this, right?
Yeah, there's the tear up of the fuel system and the fuel delivery. That's a pretty significant constraint that has to be thought through to make sure there's fuel on board. But yeah, it could be an interesting idea.
Okay, and that's a leader to another question that Thomas from New Flyer had. Is Cummins planning to provide the fuel systems, the tanks and those sorts of things as well as a part of the scope of supply?
Yeah, we would have access to tank technology. We have a joint venture with a company in Europe called NPROX. They have really, really nice IP and technology related to hydrogen storage. And so we're working to have a full system available fuel delivery system in addition to the engine.
Okay. Michelle from the National Research Council of Canada has a couple of questions asking if the engines can accommodate the use of different fuels. Can they accommodate hybrid fuels like LNG and diesel, diesel and hydrogen, etc.?
Yeah, that's a good question that comes up a lot too. We call it a fuel agnostic platform. Yeah, and that's not intended to communicate a flex fuel engine that in a given vehicle you can swap between fuels. It's a pretty significant hardware difference still with a cylinder head, engine controls. So any given vehicle is a single fuel. The platform can be used to build multiple, different fueled vehicles, if that makes sense. So it would be too costly to buy it as a diesel and then switch it out to become a new fuel. Just the economics of that individual unit wouldn't make a lot of sense.
Yep, sounds good. And then the second part of Michelle's question is, hydrogen is a highly corrosive fuel. How does the design take into consideration, and what is the impact on maintenance schedules compared to non-hydrogen internal combustion engines?
Wade, do you want to respond to the first one?
I take on that one. Hydrogen by itself is not a corrosive fuel, by the way, right? So hydrogen is not really corrosive. Hydrogen might diffuse into some of the metals, and depending on what is the kind of metal, you may or may not have a risk, right? So for example, we know from the oil and gas industry, if you have a high strength steel, the hydrogen may diffuse in there and marry with the carbon to form methane, that it deteriorate your mechanical strength. So we're doing that kind of analysis risk assessment, and it also depends on what is the environment this metal is being used, right? It's being compressed, being stretched, or what is the application of that components. Not all components exposed hydrogen needs to experience that kind of force. The other thing is, for the engine, we have this cold and hot cycle, if you will, right? So when you have the hydrogen diffusing into the metal, and when you get the combustion, normally that kind of bake out to the hydrogen. So we have spent many hours on this engine. We haven't really seen any damage because of that yet, but it doesn't mean the risk isn't there, right? So we're doing an assessment to see how we can mitigate the risk. I think the corrosive aspect is actually come from the hydrogen combustion, I believe. The hydrogen combustion, normally people have the perception hydrogen combustion product is water. You would have a lot of water. What we found is if you run lambda 2 or leaner, your water level in the exhaust can be lower than natural gas stoic. So anything we have learned from the natural gas exhaust system still applies to here. Another thing I want to point out is, for natural gas, you have the mercaptan, and for diesel, you have sulfur. Hydrogen has no sulfur. We don't expect that the hydrogen engine would have a different fuel source compared to hydrogen fuel cell. So hydrogen fuel cell require the hydrogen to be really pure, right? There isn't sulfur or other elements to make the combustion water corrosive per se. But anything we have learned from the natural gas exhaust system, I think still applies to here. Not sure this answered the question, but this is my view.
And then I can add on, the second part of the question was around maintenance. From a maintenance perspective, it looks very similar to diesel or natural gas at a system level. From the engine perspective, this has a spark plug. There's a replacement life. Otherwise, the diesel maintenance schedule looks like it applies. And then we may be able to, the idea of a DPF clean is under investigation. It just may go longer, if not, doesn't require cleaning at all. We'll see. And then Hui mentioned a good point that I just want to reinforce, that the engine can run on less pure hydrogen. It doesn't require, because it doesn't, a fuel cell can be, the fuel cell catalytic plates can be poisoned by impurities in hydrogen. It requires a very pure level to avoid that. The engine is less sensitive to impurities in the hydrogen and also in the air. It requires normal engine air filtration as well. So from a challenging environment perspective, where the air quality is bad, if you're filling up on a construction site with hydrogen, just some of those, the engine's less sensitive, I'll say, as well as cold ambient conditions. We don't see that as a challenge. And Hui, I think I've heard you mention startability too, perhaps is actually not an issue at cold ambience as well.
No. And just to that, when we're thought about the spark plug, right? Spark plug is one of the service items in there. Hydrogen has a lower ignition energy, so you don't require as much of ignition power. What we are working on is also to look at the electrode size, right? We could potentially increase the electrode size without jeopardize the performance on the ignitability of the system. That's gonna prolong the spark plug life, right? So you're gonna significantly extend your service interval or reduce the cost on the plug itself and in the downtime.
Interesting. So another question, and I think The question from Thomas is, what is the top tank temperature limit? And I'm assuming that this would be the thermostat setting on the engine and what water temperature it would run at. I could be wrong, but
you'd have to make a guess at that one, Hui, or not know. I think we talked about cooling systems, and we're saying that, yeah, we don't expect as high of a heat from in the cooling system, but I don't know if you'd know the top tank temperature yet.
So let me give it a shot. I think whatever the carbon fibers temperature limit.
Oh no, I think it's radiator, not
the radiator.
yeah, the water side.
Oh, water side. Okay.
Yeah, so water temp would be similar, probably lower than diesel.
Yes.
Right.
Okay. Okay, bit of a tangential question. David Linton from the Manitoba Trucking Association is asking, what are your views on various technologies that inject supplemental hydrogen to the air intake of compression diesel engines? Is this a reasonable approach to the technological transition to zero emission vehicles?
Yeah, so we're aware that there are third-party upfit options out there. It's not something that's necessarily been endorsed by Cummins. We're not working with any particular supplier out there. It'll likely void the warranty on the engine, so just be careful. But yeah, I don't think we have necessarily a formal response on those technologies at the moment. I mean, I like the idea in general, like the idea of moving forward with hydrogen and look for creative ways to help the industry, develop bridge technologies, but we can't necessarily endorse or talk about a specific technology.
Yeah, there's no technology out of the UK, and they seem to be focusing on last mile delivery. So I'm not sure whether that means that it's more effective in stop and go type operations more so than continuous operations. I'm not familiar with that as well. So, okay, moving over to shown in one of your first slides, the semis have shown 80 kilograms of hydrogen stored at for 500-mile range. What's the typical pressure volume? Would that be at the 700 bar to get 500-mile range?
Yes, 80 kilograms, 700 bar. Yep, yeah, that's right. And I think I saw somebody ask a question about fuel, refill time, and I'm just going to go look up the number. My mind says it's about 30 minutes to fill that system up. Okay. So 30 minutes to fill up 80 kilograms around that time.
Yeah, and that should be similar to a CNG vehicle, right? They're fairly similar, although CNGs are typically 3,000 or 3,500 PSI, so it probably takes a little longer at the higher pressures, right?
Yeah, it might be the other way around. Because that's in PSI, this is in bar, so yeah, I think that's lower pressure. It might go a little faster.
Okay, perfect. Related to the fuel delivery system, how long does it take to refuel? You talked about that.
Yep.
And Evan is asking, what is the fuel system pressure after being reduced from the tank? Hydrogen is notoriously leaky. Have there been any challenges surrounding seal and component reliability in tough environments?
So Hui, maybe the injection pressure at least. I don't know what the fuel lines have coming to the engine, but
yeah, it depends on which fuel system supplier you go with. I think up to 60 bar. At lower load, you can use a lower injection pressure, right? So that the real pressure would be with the pressure you want to control once the fuel discharged from the fuel tank.
Yeah, so there's quite a bit of reduction that goes in. The tanks might be very high pressure, but the engine doesn't need the high pressure. It's more just a capacity, packing in more fuel on the cylinders, but it's reduced pretty quickly as it runs through the vehicle.
I would assume that you're reducing right out of the tank, right? You're running a lower pressure from the tank to the engine, and then the engine's doing its thing with to deliver the pressure it needs to run.
Yeah, so the advantage of not using a really high pressure, you can fully utilize your onboard hydrogen storage, right? Onto a very low level, you can still deliver the fuel to the engine and use it.
Excellent. Another question here, is the tank standard size, or can it be customized to fit a design? You talked earlier, Jim, about different tank configurations, but trying to keep the SKUs down to basically get some volume so that the price can be reasonable, right?
Yeah, that's right. We'll want to standardize on certain nodes and not have too much proliferation in dimensions, length or probably diameter. and so I don't think we're far enough along to see. I don't know that any of the studies have been done to see, is that 5, is that 12, and and there's just cost, I mean, I guess any dimensions possible. It's all about cost.
Interesting. Another one just popped up here. What is the engine compression ratio?
Right, the compression ratio would be lower than diesel and typical natural gas. So I would say it's a range, right? So somewhere between I would say 10 to 12 to 1 compression ratio are feasible. Depends on, do you want to optimize, prioritize for efficiency and power density, right? So those are the considerations.
And that's quite a bit lower. Diesel's in the 20s, ish, 20 to 1 or so.
Yeah, diesel has a lot higher.
Compression ignition, you need that.
Yep.
Yeah, perfect. So we'll just give it a couple of seconds here to see if there's any last questions coming through. And I see nothing coming through. So with that, I'd like to thank you guys for putting on this presentation. There's in Manitoba, we have a lot of companies that build big things on rubber wheels that, are I would almost guess that our blood has a little bit of diesel fuel in it, because that's kind of where we've been, what we're used to, right? And we know there's a transition coming. And what's really what I find really interesting about what you guys presented today is this is a production ready technology in 2027. So rather than wait for whatever it is that's going to be zero emissions, we can start reducing the amount of carbon we're throwing up into the atmosphere right away using a technology like this until that other technology matures. And like you said, Jim, you're using the fuel that you're going to use if you're going to go hydrogen fuel cell anyway. So you're only going to pay for that infrastructure once. So yeah, excellent presentation. Really appreciate it. Thank you guys for putting this on today.
Yeah, thanks for the opportunity. We really appreciate you organizing this and the great group that you have together. We've got some friends out there, so we're excited that you got to hear the presentation. Contact information is on the slide. Feel free to reach out to us. We're excited about the technology. Trying to reduce the amount of carbon that goes in the air is critical, and it's the area under the curve. So let's just try not to put it in as fast as we can, and we'll all be better off. So
that's fantastic. Again, thank you very much, Jim, Hui, and Jeffrey, for your time today. And yeah, we'll for those of you in Manitoba here, look to see some information on the trip to the Mesa to the IAAA commercial vehicle show. Probably in middle of June, we should know what's happening with that trip. So well, with that, thank you very much, gentlemen, and everybody have a great day.
Thanks, everyone. Thank you. Bye-bye.
All right, bye-bye.